Hi, I'm Luke Dramko. I'm a PhD student at Carnegie Mellon University. And my talk today is about decompilers. These are tools that convert executable software into a high-level representation, which is typically C. And these are useful anytime you want to analyze a binary, but you don't have access to the corresponding source code from which it was built. So this includes situations like malware analysis, vulnerability research, and sometimes even patching legacy software. Despite significant advances in decompilation over the years, code produced by a decompiler is missing many of the characteristics which make code readable. Of course, when a compiler compiles a program, a lot of the information is discarded. There's a lot of information in source code that is there for the programmer's benefit and not actually needed for the program to run. So when that same program is decompiled, that information isn't available for the decompiler, and as a result, the decompiler just has to make its best guess. The resulting decompiled code looks significantly different from the original. For instance, consider variable names. These are very useful abstractions for programmers, but are completely useless at the executable level, so they're discarded. And the decompiler has to replace them with generic placeholders. Variable types. Most of the information about variable types is discarded. So the decompilers usually can't fully restruct types, and as a result, the resulting code looks substantially different. So clearly, names and types are two of the things that are different about decompiled code. But there's a lot more. And our group wanted to be more systematic about this. So we developed the research goal to develop a comprehensive taxonomy of the consequential differences between decompiled and original code. And the purpose of doing such a thing is to create a snapshot of the state of the field and to motivate future work in decompilation. So we've come a long way, but what work is left to do? To accomplish this goal of building this taxonomy, we used a qualitative empirical research method called open coding. And this provides a rigorous and systematic way of identifying patterns in typically unstructured textual data. We perform open coding on original source and decompiled function pairs. So basically, we took source code, compiled it, decompiled it, matched up the functions, and operated on this. The entries in our taxonomy are defined as differences with respect to the original source code. So we consider the ideal decompilation, if we had a magically perfect decompiler, the one that is exactly identical to the original source code. Now, obviously, this is not possible in general, but we would like it for it to be as close as possible. The entries in our taxonomy are defined in terms of a novel abstraction called an alignment. So aligned code fragments are those that fulfill the same role in the function. That's the intuition. We have a more fancy mathematical definition in the paper and supplementary material if you'd like to try it out. As an example, consider these functions from a few slides ago, and further consider these two function calls. These are both recursive function calls, so they call the same function. They have semantically equivalent arguments, even if their syntactic forms are somewhat different. And they occur under the same control flow conditions with respect to the arguments of the function. So we would say that these two functions are aligned. Now, the full taxonomy is really big. It's got like 52 different entries. They're arranged hierarchically, so I won't go through the whole thing item by item. Instead, I'll show you how the taxonomy applies to our running example. So as previously noted, variable names are discarded during compilation. And as a result, they're not there when the decompiler goes to generate codes that are replaced with generic placeholders. Types similarly can't be recovered. Function names are also often discarded during compilation, except maybe in situations to do with dynamic linking. So function names also have to be replaced with dynamic generic placeholders. But that's not all. The decompiled code has this extraneous variable. There's no equivalent of it in the original code. It's extra. These struct field access operations from pointers do occur in the decompiled code, but they do in a significantly different syntactic form. So they're semantically equivalent, but syntactically different. And then finally, the decompiled function returns a value, whereas the original function is void. So the two functions have different return behavior. So once we built the taxonomy, we analyzed it and came up with several key takeaways for future decompilation work. The first takeaway is that types are absolutely critical. Many issues were caused by decompilers' inability to reconstruct types. It's kind of like a downstream secondary effect. So consider this sequence of operations. We have some sort of 64-bit integer, and we're adding a fixed value to it. From context, the fact that we're typecasting it to a pointer, maybe this is a memory address, and this is an offset. And then we do treat it as a memory address with a typecast, and then we access the value at that address with a pointer dereference. So this is, as we noted before, it's semantically equivalent to a struct field access operation, but they're syntactically very different. And the reason the decompiler has to generate this kind of desugared version is because the decompiler doesn't have access to the variable type. So the lack of type recovery can have a significant impact on all sorts of other parts of the decompiled code. The second takeaway is that interprocedural analysis is likely necessary to help fix many different issues. So consider this return statement. When a compiler is compiling a function, especially if it's a void function, a compiler is free to use that, the return register just like as another general purpose register. And of course, whether or not the function was originally void was discarded. So when the decompiler goes to decompile that function, it's not clear whether a value is in the return register by coincidence or if it's actually supposed to be there and is supposed to be the return value. So the decompiler makes the conservative choice and assumes that value is actually intended to be returned. And indeed, you can't tell just by looking at this function or indeed the assembly for this function. But you can tell by looking at all of the call sites for this function in the program. And if none of them actually use the return value, then this function is likely void, or is at least effectively void for the purposes of the program. The third takeaway is actually a combination of the previous two. Recovering many important types often requires interprocedural analysis. So think like key data structures that are used throughout the program. Let's consider recovering the type of the variable A2. We see it used in this sequence of operations, which, as we noted previously, is a kind of a desugared representation of a struct field access operation. So this suggests A2 might be a struct. Further, we see the fact that this field is used as an argument to a recursive call to the same function. So that suggests that A2 is some sort of recursively defined data structure. And then on top of this, we see this happens exactly twice with two different offsets at +16 and +24, which suggests that this is some sort of recursively defined data structure with two different child nodes, so something like a binary tree. But from this function alone, it's not clear what this is binary tree of, that is, what's being stored at each of the nodes. Indeed, the true node structure actually does have several other fields, none of which are hinted at in this function. In general, you might have to analyze an arbitrary number of other functions to get all the evidence to suggest what these fields might be, so perhaps where this value is allocated or initialized or used. Kind of as a meta takeaway, both deterministic and probabilistic, so perhaps machine learning-based methods, have a role to play in advancing decompilation. Deterministic methods are attractive because they can have correctness properties that probabilistic methods simply don't. But probabilistic methods are nice in that they can predict information that was discarded by a compiler. So let's revisit the type recovery of the variable A2. Notice actually that we're starting with the decompilation, not the assembly. So deterministic algorithms have given us a really good starting point. We then use this evidence to indicate that A2 might be a struct. And indeed, this is consistent with what a struct field access operation would look like desugared. However, this is also consistent with what accessing the third and fourth elements of an array of 64-bit integers or an array of pointers would look like. And we have no real way of differentiating between the two deterministically. However, when the offset is like a fixed non-zero value, it's very often the case that this actually does end up being a struct in practice. So we can probabilistically say that A2 would be a struct. Next, we use the fact that the fields of A2 are being passed to a recursive call to conclude that A2 might be a recursively defined data structure. And another way of saying that is that the fields of A2 have the same type as A2 itself. And these constraints we can generate completely deterministically, just using program analysis. That'll give us something like this. But there's still something important missing here, names. The struct, the fields, and in fact, the variable A2 itself all need names. And because names are completely discarded, to predict kind of meaningful non-generic, non-placeholder variable names, we would have to use probabilistic methods to do that. There's a lot more interesting stuff in the paper that I didn't have time to talk about today. So there's the full taxonomy. There's the alignment formalism. Excuse me. Comparison of different decompilers. We looked at 4 different decompilers. Some deterministic heuristics for mitigating some of the issues, and then a full detailed methodology on how we did all of this. And with that, I'd be happy to take any questions you might have.